All right, so I left off the last video by mentioning that this molecule here, bromochlorofluoromethane, has handedness, right? It's chiral, and it doesn't have any symmetry operations other than identities. So molecules that are of low symmetry um, can be chiral or are often chiral. And the nice thing is now that we've rigorously, been grouping molecules via their point groups, we can talk about what point groups are chiral and which ones aren't. Okay, and so yeah, chiral molecules. I'm sure you learned this in like introductory organic chemistry. Have handedness. They cannot be superimposed on their mirror image. Okay, that's what that means. From a symmetry element perspective, this means they can't have inversion, they can't have any mirror planes, and they can't have any improper rotation axes. Okay. Now, you might have learned in organic chemistry, depending upon how it's being taught, that if you don't have a mirror plane, that means you're chiral. But that's not true. Okay, that's not good enough. Most of the time, that's good enough. But there are examples in both organic and inorganic chemistry where that is not true, where you don't have a mirror plane, okay, but you're still not chiral. So because a chiral molecule cannot have an improper rotation axis, Sn, okay? So I'll show you an example of this later. It kind of blows up some conceptions that some people have. Chiral point groups, now we can be very rigorous about what chirality is. Molecules that, well, we know the definition of chirality, but we can be more rigorous in how we can spot chirality, okay? And we can do that with point groups. Molecules that are chiral must be in either the CN, the DN, the T, O, and I point groups. Any other point group, it's not going to be chiral. So you can see most point groups are not chiral. Chiral molecules are relatively rare, right? Some terminology here, something that's asymmetric means it has no symmetry element beyond E. Something that's dissymmetric means it only has E's and rotations, okay? So yeah, molecules in all other point groups are not chiral. So yeah, CN, DNs, T, O, and I. So here's a dissymmetric molecule. It's in the CN point group, C2. It's chiral, and it has some symmetry still. It has a C2, right? But because it's in a CN group, and because it doesn't have any mirror planes or an inversion center or an improper rotation axis, its mirror image is not superimposable. So it will have enantiomers, remember? Those are the different mirror images of chiral molecules called enantiomers. But it has some symmetry still. It has a C2, right? You can see what happens. This OB molecule goes into this OB oxygen atom level OB goes into OA and vice versa on 108 degrees. This top one goes to the bottom. So you can kind of see we're spinning it like that. Here's getting to the point, an example where I said, oftentimes people learn that if a molecule doesn't have a mirror plane, that means it's chiral. But here is a molecule that doesn't have a mirror plane and is not chiral. So that line of reasoning is completely wrong, okay? This molecule is called tetrachlorospiropentane. It's a very weird molecule, but hey, it's a molecule, you can make it, and it's not chiral. It's in the S4 point group. And so because it has an S4 and an improper rotation axis, you can see it here, remember improper rotation, an S4 would be a C4 followed by a sigma H. So you would rotate this, let's go the direction of the arrow, rotate this here, okay? 90 degrees into sort of the back left, and then you would flip it across a sigma H, so that brings it down here, okay? You can see you can do that for like this hydrogen here, goes down and then goes down here, goes up and down, okay? So it has S4s, it has an S4 3 times, okay? And it also has a C2 and identity, not chiral, no mirror plane. You probably also learned in organic chemistry that asymmetric carbons are what you need to be chiral. And yeah, that's true. An asymmetric carbon, meaning a carbon with 4 unique substituents on it, will be chiral. Okay, like bromochloro fluoromethane. But there are other molecules in organic chemistry that are chiral that do not have asymmetric carbons. So for an extra credit point, email me a link to a website or a link to or structure of a molecule, or send me a structure of a molecule or something, Wikipedia link or something, to a molecule that does not have an asymmetric carbon, that's organic, an organic molecule, and that is chiral. Okay, and I think you'll have some fun looking at all the sorts of very interesting types of molecules that organic chemists can make that are chiral but don't have asymmetric carbons.